One of the applications of a quantum internet is secure communication. Specifically, a quantum internet allows us to realize quantum key distribution. So what is the problem that quantum key distribution tries to solve? Let's imagine two friends, Alice and Bob, who are far apart, and they want to communicate. But they want to communicate secretly. In particular, they are afraid that their friend Eve, who is extremely nosy about their relationship, is trying to listen in to their communication. The goal of quantum key distribution is to use quantum communication to defeat Eve's attack and to protect the communication between Alice and Bob. Secure communication has been and is extremely important in many areas of our life. Already in the past, it has been extremely important to protect secret information. For example, during World War II. In fact, a big effort that spurred the development of the computer is related to the need to break encryption schemes and to read secret messages in order to find out where the enemy is hiding. Secure communication is also extremely important to transmit bank information securely. It is also extremely important to transmit personal information. If your medical records are sent over the internet, I'm sure you might prefer that not everyone can read them.
Let's have a look at the theory.
In order to understand key distribution, let's first talk a little bit about encryption and how encryption can help to make messages secret. Let's imagine that Alice wants to send her message to Bob, and they already share a key. For the moment, imagine that Alice and Bob both have the same key to a safe. You can think that an encryption scheme works just like a safe. Alice takes the key, opens the safe, puts in a message, and sends the safe over to Bob by post. Bob, who has the same key, can open the safe to recover the message. Now, anybody in the middle, in particular their nosy friend Eve, who does not have the key to the safe, cannot open the safe and read the message. So as long as Eve cannot get into the safe, or more specifically, as long as Eve cannot break the encryption scheme, she cannot read the messages of Alice and Bob. Let's have a look at a very simple encryption scheme to see how electronic encryption schemes work. When communicating data over the internet, keys are not physical objects like pieces of metal, but they're bit strings, zeros and ones. Messages can also be written down in terms of long sequences of zeros and ones. Let's see how Alice can use her key, which is now a bit string, to produce the safe, the encrypted message, which she's going to send over to Bob. The simple encryption scheme we will consider is also known as the one-time pad. And here we have a message which is just as long as the key. To put the message into the safe, Alice is going to take the message and add each bit of the message to the corresponding bit of the key modulo 2. So what does this mean? It means that if the key bit and the message bit are the same, then the safe, the encrypted bit that she will send over to Bob, is 0. If the key bit and the message bit are different, then the encrypted message that she will send to Bob, the safe, is going to be 1. So now you might be asking, how can Bob get back to the message? Because remember, Bob should be able to use the key to open the safe and recover the message. If we have a look at this, we see that if Bob knows the encrypted bit and he also knows the key bit, we can see that these two together allow me to uniquely identify a message. For example, if the key bit is 0 and the encrypted bit is 0, then I know that the message bit must have been 0. If the encrypted bit is 0 but the key bit is 1, now I know that the message has been 1. Because remember that the encrypted bit is always 0 if the message bit is the same as the key bit, and 1 otherwise. So in this way, Bob can recover the message using the key. Now you might be asking, is it possible for Eve to break into the safe? Let's have a look at this table again, and let's imagine that we do not know the key, but we only see the encrypted bits. We see that for every encrypted bit, in fact both messages 0 and 1 are equally likely, if the key is equally likely. So if Eve sees a 0, then in fact the message 0 and the message 1 are both possible. If Eve sees a 1, but she does not know the key, then also she cannot tell whether we started from a 0 or 1, or what Alice's message has been. So you can see that without knowing the key, Eve cannot open the safe. This is a simple encryption scheme, but you see that it crucially depends on the key. Now the question, of course, arises, where does this key come from? And how much key do we actually need in order for the message to be secure? It turns out, and this is a beautiful result by Shannon years ago, that to be totally secure, we need a key that is just as long as the message. That's quite a lot of key. If we look at this very simple picture of 64 by 64 pixel, we can see just how much key that is. We can call a white pixel a 0 and a black pixel a 1. That's already 4096 bits of key that we need if we were to send this image. Of course, in daily life, you might want to send much longer pieces of data, much larger images, and even videos that are thousands and millions of bits. So we see that to be absolutely secure, we need huge amounts of key. Practical crypto systems that are used in the real world nowadays use keys that are much shorter than the message. So they don't offer the ultimate guarantees of security, but rely on the fact that yes, the key might be short, but it might be difficult for Eve to interpret the encrypted message in the right way. Or more precisely, it might take Eve a long time to figure out and compute what the message was. It is known that many of these classical encryption schemes are in fact broken once we've built a quantum computer. So if Eve buys a quantum computer tomorrow, she can read today's messages. But there's even now actually no mathematical certainty of how difficult it actually is to break these existing schemes on a classical computer. Given the key is so important, you can ask yourself, where does it come from? Once we run out of key, can Alice and Bob make more key? It turns out that using classical communication, so sending bits of the classical internet, there's in fact no way to make more key. And there's an easy way to see that this is not possible. If Alice sends a blueprint for making a key to Bob, classical bits over the internet, then surely Bob should be able to recover the key. Because we've already seen that without knowing the key, Bob cannot get into the safe and learn the message. defeating the whole point of their conversation. But now, because classical bits can be copied, of course anyone trying to listen into their conversation can also intercept the blueprint for the key, and therefore also make a copy of the key, just like Bob. So the fact that classical communication can be copied means that if Bob should be able to learn the key, the eavesdropper can also learn the key. And therefore we cannot produce more key.
How can quantum solve this?
Now the cool thing about quantum communication is that actually qubits cannot be copied. And this is exactly what lies at the heart of quantum key distribution. And quantum key distribution always allows us to make more key. To perform quantum key distribution over long distances, we need a quantum internet, with which Alice can now send not classical bits, but qubits over to Bob. Roughly speaking, to do quantum key distribution, Alice will send many qubits, one at a time, over to Bob. And because qubits cannot be copied, and in fact we can even check whether Eve tried to make a copy, Alice and Bob can now verify by talking to each other over the classical internet whether Eve tried to make a copy, whether Eve tried to listen in, and whether the key is secure. Quantum cryptography is in fact secure even if the attacker has a quantum computer. Even if Eve would control all the rest of the universe, nevertheless she cannot listen in to the secret communication between Alice and Bob. Quantum key distribution is actually already a reality at short distances. And the reason for that is that it's relatively simple. Alice and Bob only need to prepare and measure a single quantum bit, 1 qubit. Short here, however, means roughly 100 kilometers. It is a great challenge to send qubits over long distances. And at QTech, we are working on a quantum internet that will ultimately enable long-distance quantum communication between any 2 points on Earth.